Okay, today we'll be talking about a very important topic, and that is duality in linear programming. So please listen carefully and pay attention to what we'll be discussing today. Before that, I've just put up some more examples on LP formulations because in your exam or quiz, you may expect some problem given to you, which you should convert into an LP form. So I've got some more for you over here before we get into duality, okay? Do we have any questions regarding our previous lectures? Any questions? No?
No question.
Good. So I'm hoping you all are studying, and that's the only reason why you don't have questions and nothing else. Okay, so let's look at an example where we have a company that makes some product, okay? And for example, let's say that there are 4 months and you know that you know in advance the estimated amount of product or demand for that product for each month. So the first month, the expected demand is 1,000 items, then 800, 1,200, and 900 items, okay? And that company has a capacity of like 800 per month in the regular time. That means you're in regular working hours. So there, for regular hours, like there you can have 800 hours in a month. And if you have overtime where your company works overtime, it has a capacity of making 200 more items every month, okay? And then the cost of corresponding to each of these different times is also given over here. So if you produce the product in regular time, it takes $20 per product or unit. And if you produce it in overtime, it costs more because you have to pay for more labor, probably more electricity during nighttime and all that. So it is more expensive at night during the overtime production. The thing that the company can do is it can produce some the units in 1 month, and if that month the demand for that month is satisfied, then it can actually store it and use it as surplus units for the next month, okay? So what it can do, it is can carry the inventory to the next month. But the thing is, for storing that unit, they have to pay an extra fee, which is $3 for per unit. So if you want to store the unit for the next month, you have to pay $3 for each unit that you store. If you want to store it for 2 months, then it will become $6 and so forth, okay? So what we want to do is we want to formulate this. So what is the problem? The problem is obviously try to minimize the cost required to satisfy this expected number of items or units per month. So I should see what is the cheapest way so that I can at least produce 1,000 units in month one, 800 units in month two, 1,200 in three, and 900 in four. Okay. So to do it in an LP form, this is a slightly different form than we have seen earlier over here. As you see, the decision variables are denoted by xi, yj, and ij. So what are the xi's? Xi's is the amount that you produce of the particular product in regular time, in month I. So in the first month, if I produce 50 of those products, so it would be x1. In month two, it is x2, x3, and this is the amount you produce in the regular time, okay? For the overtime, the amount you produce in the month J would be denoted by Yj, okay? And Ij is actually the amount you carry over to the next month, okay? So Ij means at the end of the month J, you carry the amount to the next following month, all right? So with these three variables defined, we can very easily come up with our objective function, which is obviously minimize the cost. So we have $20 per unit in regular time and $25 per unit in overtime. So we have 20 times the sum of all the xi's. How many xi's will we be having? There are 4 months, so there'll be x1, x2, x3, and x4. So 20 times the summation of all xi's. Similarly, 20 plus 25 times the summation of all yj's, which is the product or the production, the number of items you produce in overtime production. plus the $3, which is a storage cost for storing the extra items that you produce in the month J, and you want to carry it over to the next month. Okay, so since if, for example, I can take over here, J can take values from of 1, 2, and 3 only. It cannot take 4 because in month 4 there's nothing else to carry over. So you can carry from 1 month to month 2, month 2 to month 3, and month 3 to month 4. Okay, so that's why you go from J from 1 to 3. And now let's look at the constraints. The constraints over here are very interesting. So now if you see, what it says is the amount you produce in regular time, which is X1, plus the amount that you produce in overtime should be equal to 1,000, which is the requirement for the first month, plus I1. I1 is plus the amount that you would move over to the next month. Is it clear? Do you understand the constraints, guys? If there's any question, just stop me, okay? Because I'll keep talking and I'll stop only if you stop me. So this constraint says that whatever I produce in regular and overtime should be equal to the estimated demand. That is for that particular month, which is the first month, and the amount that I would be carrying over to the next month. Okay. Then the second constraint is now the amount that I carried from the first month plus what I produce in overtime and regular time should be equal to the demand I have to satisfy, plus the amount that I will be additionally producing for the next month, which is I2. And similarly, you have it for the third month. And for the fourth month, you see that we have what is remaining from the third month plus X4 and Y4 is equal to 900. There is no I4 over here. Obviously, Xi and Xy's, X's, Y's, and the I's, they are all the number of number of products, so it cannot be negative. So you have this default constraint, which is greater than equal to 0. Okay. So with that said, okay. And also, yes. So the other thing that you have to keep in mind that the Xi's, okay. What is this? Yes, this constraint is that the number of hours, the capacity, okay, per month. Okay, so per month, I can only produce 800 of those units in regular time and 200 of those units in overtime. Okay, so this is another constraint that you have to consider over here. These two constraints. This I is for all I's from 1 to 4, and this J is from all J's from 1 to 4. Okay. So if you look at this constraint, this formulation, this is a LPP problem formulation, no doubt about that. But then you look at the number of decision variables. How many decision variables do you see? We have 4 here, which makes it 8, 9, 10, 11 for the I's. So we have 11 decision variables, okay? And we will be having how many constraints? 1, 2, 3, 4. These 4, and then we have 4 over here, and we have 4 over here. 4 3s are 12, so we have 12 constraints without considering the default constraint. Okay, so you see you have 11 decision variables and 12 constraints. That's a big problem. Okay, a big problem is a big problem in terms of size to solve. So let's see what would be another alternative formulation. So if such a question is given in the exam, some of you may formulate it as this, but some of you may find a different way to formulate it. Actually, this problem can be formulated in multiple ways. So let's look at another formulation. So what it's trying to do is we are trying to reduce the number of decision variables. So one other option alternative is try to get rid of these IJs. Okay, how can we do that? By rewriting the constraints as over here. Instead of writing this constraint, which is over here, the first stamp draw. This constraint, this guy, what we can do is we can say, okay, X1 plus Y1 should at least be 1,000. Okay, and then instead of this constraint, what I do is instead of carrying this I1, I would say now what we had in the first constraint plus the second constraint should be at least greater than or equal to the 1,000 demand for the first month and the 800 demand for the second month, 1,800. Okay, so I can do that. And similarly, in the third case, I would say, okay, now take these two equations, okay, and add the y1, y2 and add the x3 and y3, and that should be greater than equal to, now we had 1,800. What was for the third month? The third month was 1,200. So 1,800 plus 1,200 would give you 3,000. Okay. And therefore, and finally, the last one for the last month would be 3,000 plus 900, which would be 3,900. And these two constraints remain the same. We cannot do anything about that. So now what we have done is we have reduced the number of variables. So we have got rid of the ij. Okay. Now this is again another formulation, LP formulation. And yes, so what we did not change is the objective function. The objective function, we have to get rid of this ij. And the way you do that is to write actually this in terms of these equations that you've got. That means x1 plus y1 minus 1,000. Okay. This guy over here. Plus the second equation. This equation, okay, which would be x1 plus y1 plus x2 plus y2 minus 1,800. So you bring this 1,800 to the left-hand side, plus this equation. And when you do that, actually what you're doing is replacing this greater than equal to with an equality. So there is some value over here. So you take this on this side, and whatever is remaining is actually that ij, which we have eliminated, okay? And therefore you would get this relatively longer objective function, okay, if you plug in all the four constraints. And now what we have done is we reduced the size of the problem by reducing the number of variables to 8, and all the what is this called? Over here we had equality constraints, but here all the constraints are of type greater than equal to, except for these two, which is less than equal. So they are inequality constraints. All right. Now, the question is, which one is better? Better in terms of like solving the techniques, using the techniques that we have studied so far. Okay, so if so let's say that we have two alternative representations for a problem, and if in both the representations, the problems, they have the same number of constraints. So if you have, say, 4 here and 4 there, then we will select that formulation which actually has lesser number of decision variables. Okay, so because the lesser the decision variables means the smaller your table if you're using simplex or a method or BigM method or two-phase method, and therefore it's easier to solve. Okay. So, and also now that's about the number of constraints. Okay, now let's look at the types of constraints. In general, it is much more easier or preferable or faster to solve problems which have inequalities rather than equalities. Okay, and obviously we know that we can convert any equality to inequality. We have seen that before in our slides last, I mean, 1 or 2 weeks ago. So preferably we would like to have problems with fewer variables if the number of constraints are the same in the alternative representations. And also we would prefer to have inequality constraints rather than equality constraints. Okay, so keep that in mind. Now, another thing is that interestingly, the same problem can be represented in yet another form. Okay, and this is the form, and I want you to spend like 2 minutes to go through it, and I'll ask someone to explain it. Okay, any volunteer?
I think it's quite complicated.
Is it?
I-
Really? Let me
Sorry,
see.
for example, here x111.
Yeah,
Like how it would
I
it
just
would
want to
be
see
like
whether I can
ij.
tickle your minds or not. I'm trying to tickle your minds.
it's just what does it mean production type K?
Well, it means regular time or overtime. One is regular, two is overtime.
So we can produce in months one to meet the demand of months two. Yes.
Okay, let me do it. Okay, listen carefully. So what I can do is instead I can define a decision variable which actually has three subscripts. Okay, I, J, and K. So it is so what does this variable denote? It denotes the amount of the units that you produce in month I, in like any month I, and that amount is actually used or produced to satisfy the demand of the month J. Keep in mind that over here I could be equal to J. Okay, and the way the way the product is produced is either regular time or overtime. So K is 1 or 2, where 1 is regular, 2 is overtime. Okay, now let's look at this. The first constraint tells me it is X111 means the amount of units that I produce in month 1 for use in month 1, okay, using regular time production, plus the amount of units that I produce in month 1 for the demand of month 1 using overtime production. Okay, so this two should be equal to 1,000. Is it clear?
Yes, it's clear now.
Okay.
More clear.
Yes. Now let's look at the second one just to make it even more clear. The amount I produce in month 1 to satisfy the demand of month 2 using regular time, and the amount I produce in month 1 to satisfy the demand of month 2 using overtime, plus the amount I produce in month 2 to satisfy the demand of the same month 2 using regular and overtime. So this is like the carry IJ that we had earlier, and this is the production for that particular month itself. And this should be equal to 800. Similarly, you do the same thing for this. Is it clear? Now, keep in mind the question that you may ask is, can I carry over from more than 1 month? And the answer is yes. We are assuming that I can produce in month 1 for month 3, because I know the estimated demand in advance. Okay, and I'm using overtime and regular over here, regular and overtime, plus the amount I produce in month 2 for month 3 using regular and overtime, plus the amount I produce in month 3 for month 3 itself using regular and overtime. And this total should be equal to 1,200, which is the estimated demand for the third month. And similarly, you do the same thing for the last month, which is month number 4. And what you do is, okay, so now the XI and YI change to this. So now the amount that I produce in month 1 for month 1, or I can say this, the amount that I produce using regular production type should always be less than equal to 800 per month, right? So the amount I produce in month 1 for month 1, month 1 for month 2, month 1 for month 3, and month 1 for month 4 using regular type should always be less than equal to 800. This is a production of month 1. Okay, keep that in mind. Now, when you go to month 2, you do the same thing. 2 for 2, 2 for 3, and 2 for 4 should be less than 800. Similarly for 3 and for 4. So the last one will be the amount I produce in month 4 for the month 4 using regular time. And you do the same thing for overtime. Okay? And obviously, since this is a number, and number should be either greater than or equal to 0. Now, is it simple?
No,
Yes.
it is. Yes.
Any questions?
It means like for the value of k equals to 1, it means regular time, and
Yes,
of k equals 2, it's overtime. Yes.
yes. Okay. So once you're done with that, and obviously we have the default constraint, which is all of them should be non-negative. And similarly, you just change the objective function. The objective function would be the amount you produce in regular time, which would be amount for 1 month. So all those variables which have number 1 in their last subscript. Okay, so everywhere that you see the 1 in the last place should be put here, plus 25 is the amount that you produce in overtime. So overtime is the last number, should be 2. Okay, and what else is there? Let me clear this. And 3 is the amount you carry over to store for the next coming months. Okay, so I can produce in month 1 and I can store it for month 2. Okay, using either regular or overtime, doesn't matter. Or I can produce in month 2 and store it for month 3. I can produce in month 3, store it for month 4. Okay, this total, that means if the carryover is only over 1 month, for 1 month, that means you multiply by 3. But if you're carrying over for more than 1 month, that means, for example, I'm producing in 1 month for month 3, that means I'm skipping 2 months, skipping a month. You have to add 2, right? So there's a 3 plus 3, which is 6. So for 2 months, it will be 6 times this. Okay, so when the difference between the first 2 numbers is 2, it is 6. When the difference is 3, it is 9. That means I'm carrying for 3 months. So 3 plus 3 plus 3 would be 6, right? And this would be your objective function, which is a minimize the cost. Now over here, you see that, again, we have now actually more number of variables, which is 11 variables and 12 constraints. And obviously, this is not efficient, but it is another formulation which is correct. Okay, so what I'm trying to do, or trying to show with this example, is that one problem can be formulated in many ways. You should be smart enough to come up or select a formulation that actually gets you to the answer quicker, okay, more efficiently. In the exam, don't say, okay, I formulated using this, but it was too long to solve it. Obviously, it's too long to solve it. So definitely there should be another way. So you make sure that you practice enough to convert a problem statement into a mathematical LPP formulation. Okay, then again, what I did over here is now I've provided you another example of simplex method, which we saw very early as a first method before Big M and two-phase. And over here, so the simple problem has, well, the reason why I'm reiterating over this is because in duality, I'll be using the same example 2, to show that, to obtain the dual of this problem. Okay, so just to refresh your memories, we have this problem of this form. Okay, maximize, let me bring it here. Okay, so if I want to convert it into a standard form, what I would do is I would say, okay, this is maximize, keep this as such, this is less than equal to, so add a slack variable over here, which is x3. Similarly, over here, we add another one, x4, so x3 and x4 should also be greater than 0. Great, good. And then in the simplex method, how we start by putting the by finding the basic feasible solution. That means x1 and x2 should be set to 0, and x3 and x4 would definitely be 5 and 12. So that would give me my, so if I call this guy my objective function as z, okay, so z would be equal to 0. So we are trying to increase the value of z in an iterative manner. Okay, do you remember all this, guys? Are you practicing? No one is practicing? Only I am practicing? Please make sure you practice enough. Search, look for different sample questions on different websites from different universities and try to solve many problems. Okay, you need a variety of problems to actually get hold of it and do it quickly in your exam. So, okay, we go for the first iteration where actually we first identify the basic variables over here. So the basic variables are the x3 and x4, and we write them in terms of the non-basic, which is x1 and x2, which we had set to 0. Okay, so we bring this to the left-hand side, there are others to the right-hand side. And z is the objective function. So I won't explain it too much because you guys already know this. I've written it in words so that you know how we are setting the value of x1 and x3 and how do we choose them. Like, why do we choose x1 before x2 for the next iteration? Because if you look over here, the coefficient is larger than this coefficient. So you choose x1 as the element that would be entering, and then after that, based on that, you have to take the, what is that called, the ratio, and you see that which element would be leaving. Okay, so you just take a look at this. I have explained this earlier, so I won't waste time doing that again. And then you get your second iteration where now actually you see over here x3 is there. It's x1 that is leaving, and it is who's come x4 that is entering. Okay, so you see x4 has come inside and x1 has gone outside. So x2 and x4 are now the non-basic variables. Okay, and similarly now when you have that, then again you check the value or look at the coefficients of the non-basic variables and try to find the next entering and leaving variable, and you keep doing this, I don't know for how many iterations, until you at some point z you get x1 is equal to 2 and x2 is equal to 3 and z is 27. The reason why I solved this using simplex is because now you keep this answer in mind. This z is equal to 27, actually this solution. Okay, and I'll show you in the dual how it actually we get to the same solution when we have the dual formulation. Okay, so solve this using simplex. It's very straightforward, and just keep this in mind. So the z, the optimal solution for this problem was at 2 and 3 with value 27. Okay, now again, as I said, we use the big we use the big M method or the two-phase method when the problem, the constraints in your LPP problem are either equality or greater than equal to. In other sense, we use these two methods when we have actually the artificial or auxiliary variable included. Okay, so again, if you look at this problem over here, given to you over here, first we have to convert it into the standard form. So it means that first make everything equal to, that means you minus and this, and then so now the question is, okay, so what happens if you may ask me, okay, why don't I just put x1 and x2 equal to 0 over here? Okay, let's do that and see what happens. If I just do x1, x2 is equal to 0, it would give me x3 is equal to -8 and x4 is equal to -12. But we have this constraint that they should be non-negative. So x3 and x4 cannot be negative, right? And that's why we do not just straightforwardly just set the x1 and x2 as 0, and that's the reason why we introduce what is known as the artificial variables. So now we have to introduce a1 and a2 to the constraints given over here, and in big M method, when you do that, you have to also write the term minus m times a1 minus m times a2 in the objective function. So do not forget this. Okay, for every artificial variable that you add, you have to add the term in the objective function. We added a1 here, a2 here. So you multiply it with m and take the negate value of it and add it to the objective function. Is it clear, guys?
Yes.
Good, and obviously m should be some very, very large number, something close to infinity. Now, table. The reason, again, another good thing that I want to show you in this lecture is that a different structure of the table. So probably if you are looking at other videos from other, like in YouTube or other universities, you may see something called a CJ minus ZJ, and you may question that, okay, oops, what is this? You may question that, okay, what is this supposed to mean? Okay, so this is another formulation, another way to write the table in the big M method. Quickly, I will just tell you. So these are the decision variables, whether they are in the actual problem, the surplus variables, the artificial variables, and the slack variables. So all the variables that you have in this formulation should be put over here. So for example, over here we had x1, x2, a1, and a2, and x3 and x4, right? So we put all of them over here. Okay, above them we put the coefficients of those values. So in the objective function, the coefficient of x1 was -3, -4, minus. Okay, so we just put the coefficients up here. Okay. Then on the left hand side over here, you would see the variables that you have to now add, the artificial variables. Okay. So the artificial variables were A1 and A2. So you write them over here, and their values were minus m and minus m as seen in the objective function. Okay, over here we have the left hand side. Left hand side means basically this the b vector. Oh, sorry, not the 0. Sorry, 8 and 2. Okay, so it is the left right hand side of the equation, the constraints. Okay. Where's it? Yes. So we have over here 8 and 2. So this is corresponding to the artificial variable A1, which is in the first constraint, and artificial variable A2, which is in second constraint. And theta basically was the ratio between the pivot column that you choose and the number over here. So the ratio is given as theta in this table. So now what do we do over here? The question is, how do we select our, what is it called, our table? How do we do this? Okay. So the first thing is, after you draw these two lines, after you make this table so far, you draw a line and then you write something called Cj minus Zj. What is Cj minus Zj? In this example, it is 5 times or minus m times 5 plus minus m times 2, which is minus 7m. Okay. That would be Zj. So minus Zj would be 7m, and Cj would be minus 3. So 7m minus G. So it means that the sum of the products of these two plus minus this guy. Okay. Or I would say that this guy, okay, which is our what is this? So this is our Cj, the coefficient of the decision variables in the objective function, and this guy that we obtain over here is our Zj. Okay, is it clear? So if you look at
Yes.
the next one, you have minus 2m minus 3m, which is minus 5m, and since it's already negative, so it becomes 5m minus 4, which is the Cj of x2. You write it over here. Similarly, you do this. So minus m times minus 1 is m, and minus m times 0 is 0, and this is 0, so it would be minus m. And you do the same thing for all of them, and you get this row. Okay, now the rest is similar to what we have seen before. Take the value which has the maximum magnitude. So this m is infinite, so 7 times something infinite is obviously bigger than 5 times something infinite. Not when I say infinite means not real infinite, is close to some very large number, and therefore we choose this column as our pivot column. Okay, and then what we do is we divide 8 by 2, which is 4, and divide 12 by 5, which is 12 by 5. Okay, and since this is lesser than 4, we would choose this as our pivot column, and therefore this green number, the number encircled in green, is our pivot element. Is it clear? And what do you do with the pivot element? You try to make this 1 and every other element in the column to 0. So this 2 should be made 0, and this should be made 1. You do that by the row elimination operations, and you would get this in your next iteration, and you repeat the same thing. So you do Cj minus Zj, and then you find the value which has the greatest impact, positive. Okay, this should be a positive number. If it's negative, you just ignore this. Like minus m, you don't care, only this. And so between this and this, you choose the one which is greater, which is this, and you keep doing that until you do not have any positive value in your Cj minus Zj row. Okay, since all of them are negative, therefore we have got the optimal solution. So the optimal solution would be, where is it? Okay, so it would be x1, x1 here, x1 is equal to 20 by 11. X2 is equal to 16 by 11. Okay, and the z value that you would get would be a negative value because you started out with this. You did not do the minus thing because, as I told you, if it's maximized, oops, sorry, you take everything over here, so there should basically be some z is equal to z. So therefore, you take everything to the right-hand side, and therefore, if you take everything, this will be positive. But since we didn't do that, we just directly started with that, your answer can become negative. So if it's negative, it means it's a plus. You have to take the positive of this. That's why you get 124 by 11. Now, the same problem, and I want you guys to try this out to make sure that you actually see that you can solve the same big M method. You can solve the problem using big M method as well as the two-phase approach. So the two-phase approach will also give you the same answer. Okay, so please try it out, and doing so will help you understand that actually both the methods are the same, and the difference is what I talked about last time. Any questions?
I think
No question.
Okay, so so I have a question for you then. The question is that, so in LP problems where we have equality and greater constraints, is it always necessary for us to add an artificial variable? Answer. Do we always have to add an artificial variable?
I think no.
You think no. And can you tell me why you think no?
It's hard to elaborate. Sometimes is it already in the standard form, so we don't always need, and we can we don't
Because
always
the
need to add
examples that we have seen so far, in those examples, we saw that we have always added an artificial variable. I mean, there's no harm in always adding one. In the end, it will become 0. But the thing is, can we reduce, or can we come up with a way to identify or determine whether we have to add an artificial variable to a constraint or not? Okay, and there's a there's a small trick to this, and the answer to this question is no. You do not always have to add an artificial variable to constraints of the form equality or greater than. And I'll tell you how you identify that, okay? Let's do the best way is to look at it through an example. Let's look at this example. This example given over here, okay, this guy. Okay, so what you want to do is convert it into standard form where everything is equal in the form of equality. So in equality, you would get basically this is okay, and you just add a minus x3 over here. This becomes equal, and this becomes equal. Now what you do is you write the coefficient matrix. Coefficient matrix means you take the coefficients of the constraints, okay? So the coefficients of the variables in the constraints, and you make the matrix. So 2, 3, and x3 is 0, 5, 2, minus 1. So this is called the coefficient matrix, okay? Now, the thing is that over here, what you have to do is you have to see whether you can find any identity matrix within this matrix. Do you see, and you know what an identity matrix is? 1, 0, 0, 1 is an identity matrix. So if you see anything in the form of an identity matrix in this coefficient matrix, okay, then what you can do is you can then reduce the artificial variable. You do not have to include it. But if it's not in the, if you do not see any identity matrix, it means that yes, you have to include an artificial variable for each what is it, constraint. Okay, do you see that? So since we do not find variables with coefficients as in an identity matrix, we have to add two artificial variables, a1 and a2 over here, okay? And on doing so, let's do that. So then I added a1 and a2 to these two constraints, and we start with obviously a1 and a2 as our basic variables, okay? Is that right? Because that's what you saw in this. So a1 and a2, if you see on the left-hand side, they are our basic variables. And you can solve it using two-phase method or the big M method. Okay, so that is one example. So in that example, we saw we couldn't identify any identity matrix. So that means we have to definitely add two artificial variables. Okay, now let's look at another example. This case, let's write it in the standard form. This is greater than equal to 11. So you will have a minus over here, which is our surplus variable. And this is our standard form, right? Let me see. Okay, let me use my pen. And now when you do that, you write the coefficient matrix of the constraint. So you have 2, 3, 4 is where is 2? 2, 3, 1, 4 is 0, 5 is 0, 5, 2, 3 is 0, 4 is 1, and minus 1. Okay, and if you look into this, you will see that there is a part of this matrix which has an identity matrix form, which you see over here is x3 and x4, right?
Right.
Yes. So what we can do is over here, we do not need any artificial, what is that called? Variable, because we have this, and therefore we can choose x3 and x4 as our basis or our basic variables, and we can start working with that. Is it clear now?
Clear.
Good. Try it out.
So
But if the
there's
question
just
is,
one.
if you add a variable, let me just say this and then I'll get to you. So if you do not want to test this, so for example, if I wouldn't have told you about this and you would add artificial variables as based according to the rules that we studied earlier, it wouldn't matter. Okay, it's not that it would not work. It would work, but you are just adding variables and taking extra time. You could have done it without doing that. So this is just a trick. Yes, please.
So if we just see in any place, any kind of identity matrix in our coefficient matrix, so it means we don't need to add artificial variables anywhere, or is it just?
It means that you do not have to use artificial variables, and you can use, because artificial variables in the Big Dem method or two-phase method are actually your basic variables which you start off with, right? So over here, you do not have to start off with that because we already have identified the basic variables as the one which are the one which form the identity matrix. In this case, it's x3 and x4. Okay, so you can put x3 and x4 on the left-hand side of this table, x3, x4. Oops, sorry. x3, x4, and you can start working.
Okay, thank you.
Good. Let me see, have I missed anything? Okay, you do not need artificial, yes. In the second constraint, what is it saying? The second constraint, if the second constraint was something else. So it's saying, okay, now let's assume that this second constraint, instead of one coefficient of 1 over here, it had 2 over here. Okay, but what we can do is we want to obtain this identity matrix, right? So I could have rewritten this as this, right? I divide the whole thing by 2, so I get this. And when I do this, I then convert it into this form, which is the standard form. I would still, so we write it as this, then we add a surplus variable x5 as before, and we still see that I was able to make it into what is this called? Identity matrix, right? So instead now I have 5 by 2, this is 1, 3 is 0, 4 is 1, and x5 is -1, so it's say -1. So I was able to actually, by doing this division, I set this as an identity matrix, which otherwise, if I wouldn't have divided by 2, it would have been, there would have been a 2 over here. And so you would see that this is not an identity matrix, and you would say, no, we cannot solve it, okay? I mean, you can solve it even if you, by mistake, put an artificial variable. I'm not saying you cannot do it, but you're just, doing the not wrong way, the long way. You're taking too much time to get to the same solution, okay? So you have to try to get, so the first thing that you would do is, once you have the standard form, okay, with everything in place, with the surplus and slack variables in place, try to see whether you can reduce or you can obtain an identity matrix. If you can, then that means you have found your basic variables, and therefore you do not have to start off with A1 and A2 as your basic variables, okay? Хорошо? Good.
Хорошо.
Good. Okay, let me also tell you about degeneracy, which is a problem that may happen during the simplex method and how it occurs and what is, I mean, there's no solution. It just, you have to be careful with it. And then, well, I wanted to tell you, we still have time. Okay, degeneracy. So degeneracy is a situation that occurs when you're using simplex method, and this is actually that situation where you're actually doing additional iteration. That means you keep iterating to improve the z value, the optimal objective function, but we see that the objective function just doesn't improve. It's the same, even though you're always, you know, finding and entering an exit, leaving variable, and you do that, but the z value just remains constant. It doesn't improve any further. So that is known as degeneracy, and it occurs. When does it occur? When do you have a degeneracy case in your table, in your simplex method? It occurs when this ratio, remember this ratio thing that I talked about, 8 divided by 2, 12 divided by 3, 4, 4. In that case, so it occurs whenever the ratio, whenever you get a ratio of the same value, whenever the two values of the ratio are the same, okay? And no matter which one you choose, it will always result in some extra steps. Like, for example, you see over here, you take an extra step. Over here, you take an extra step, but the value of z is not changing. It's 16, so it's not improving, okay? Over here, you see from 12, it became 16, but over here, it's 16. And again, if you do the same step, you'll get 16. So I could have stopped over here rather than doing one more iteration, but I did not know how to do it because as you see over here, I have 1 by 3, which is still positive. That means I have an entering variable. I have found my pivotal column, okay? But still, I keep doing this until all of them are non-positive, okay? And then I see, oops, but still the 16 was the same thing that I got in my previous iteration. Why didn't I stop over here? So this case is called degeneracy, and that reason is because in the previous case, the case before that, the ratio that I chose were 4, 4, and I arbitrarily just selected the second one. I could have selected the first one, and again, it would have given me the same extra iteration. Okay, so when such a case occurs, okay, it may, so what you do to avoid it is that you don't do anything. You have to use the simplex method until you do not have any positive term remaining over here. You keep doing it, but in the end, you will see that at some point, the z value doesn't change. It's 16, and it will remain 16, even though you have successfully completed the simplex method, but you see that the value doesn't change, and that's because of this tie that exists over here. Is it clear? Yes, guys?
Yes.
Okay, please, if it's not clear, just tell me. I will repeat again. I'll repeat myself. Just let me know. So degeneracy is a case when you're using simplex table or simplex method, and the case when you take the ratio between the pivot column and the left-hand side value, the B column vector, and you see that there's a tie. There are more than one rows which have the same value, and you arbitrarily just select one of them. So at some point, you would be making some extra calculation because the simplex method asks you to keep continuing until there is no positive term in your zj minus cj row. And so I stop over here, this last row, oops, sorry, this last row over here. But over here, I see the z value is 16, which was the same as the previous step. Why did I have to waste more time doing this and to get the same value? Well, because of the degeneracy case that appears over here. Okay, good. Introduction to duality. This is a very, very interesting problem, and you cannot imagine how many types of problems that seem to be unsolvable can be easily solved using duality theorem. Okay, so again, we will begin by looking at an example. This is the example that we saw earlier, so I'm rewriting it over here. We have maximized some objective functions subject to two less than equal to constraints, and we have two. So over here we have two decision variables x1 and x2, and two constraints numbered as 1 and 2 over here. So let's say that we do not know how to solve this, even though we have solved this earlier, the answer was 27. Let's say we do not know how to solve this guy, okay? So there exists some optimal value, let's say Z star, okay, for this problem, okay, which we have already found. But now without solving it, we want to see how whether we can find it or not, okay? Now let's try to see, okay, so Z, there should be a bound, right? So since we are trying, so Z is initially in that problem in simplex method, what we did is we started off with the basic feasible solution, and we saw that Z would be equal to 0. So Z is 0, then we are trying to increase it to some value. And so there will be some upper bound on it. So that would, there will be some optimal value. So let's say Z star is that optimal value that we are trying to get to, okay? This is Z star. So what we are trying to do now over here to explain the duality theorem, I'm trying to find an upper bound, and from up, I get towards Z star, okay? So I want to find an upper bound. What is the maximum value Z can have, okay? Obviously, the maximum value Z can have is infinity if we do not have this bound, but we are trying to lower that bound, okay, to some countable value. So, okay, I mentioned that actually over here, the trivial upper bound for Z, without considering this constraint. So if we didn't have these guys, obviously Z would be infinite, positive infinity. But now using these two under the influence of these two constraints, let's see how we can find this some meaningful upper bound for the Z value. Okay, do you understand what we are trying to do, everyone?
Yes, for now.
Good. So let's look at constraint 2, this constraint. Let me multiply this guy with 3, okay? And I'll tell you why I'm doing it. Multiply the whole thing by 3. So you'll get 9x1 plus 6x2 less than equal to 36. So basically you will get this new constraint. This is the same as this, right? Now, and we also know that x1, x2 are non-negative. So is it right that I can conclude that given this constraint number 2 and the objective function, this is true? That means the objective function is less than equal to 36. Can I say that?
Yes, technically.
Yes. Why is that? Because this part is greater than this part, right? No,
Yes.
so no matter what values I plug in for x1 and x2, 9x1 plus 6x2 will always be greater than 6x1 plus 5x2, right? As long as x1 and x2 are non-negative. So as long as this holds, that means, and since 9x1 plus 6x2 is less than equal to 36, it's bounded by 36, I can say now my Z is also bounded by 36. So now what I did is that Z value, instead of infinity, I have reduced it to some Z star. I can't call it Z star yet. Let's say this is our optimal Z star. Okay, from 0, we are going to Z star. So now I've got an upper bound of 36. Okay, so I'm saying that obviously the solution will not be more than 36. Okay, is it clear?
Yes.
Okay, and now did you understand why I multiplied 3 to the constraint 2 in order to make it some value which would give me a greater value than the objective function?
Can we do it the same with the first constraint, like
We're going to do it.
multiplying?
Hold your horses. You're going to do the same thing.
Okay.
Okay, now this is to answer your question. Now multiply the first constraint by 6. And by doing that, I would get this. Right? Now, obviously, again, this guy, the objective function would be lesser than this guy, the left-hand side, and therefore this is also bounded by 30. So now I have reduced 36 further 30. So I'm trying to make a more tighter bound, upper bound. Do you understand what I'm trying to do using the constraints?
Yes.
Good. So now we know that it is even lesser than 36, and I'm saying, and the two constraints guarantee that the optimal solution is even at least at most 30. Okay. Now again, I want to reduce 30. I want to see if I can reduce it any further. If I multiply the second constraint by 2, which is the second constraint, this guy, by 2. So this will give me 6x1 plus 4x2 less than equal to 24. and add it to 1. Okay, and then after I multiply this by 2, I add this to constraint number 1, and that would eventually give me this new constraint. I'm trying to come up with combinations where the left-hand side would be greater than the objective function of mine. And I see that yes, and it gives me 29. And since this is greater than the objective function, so objective function is again bounded by an upper bound, which is lower than 30, which is 29. Is it clear?
Yes.
Okay.
Yes, it's
So now you can ask me, okay, what's the point of doing this? Why am I like doing this? If probably maybe some of you, if I wouldn't have explained, would not see the intuition of the constant or the impact of the constraints. But now that we know how the constraints behave, let me now try to take it further. Now, what do we understand by what we have seen so far? So I'm saying that if I multiply the first constraint, which was over there, by some A1 value, which is positive, which is non-negative, not positive, which is non-negative, and I multiply constraint 2 by some A2, which is greater than or equal to 0, then I would get those two constraints as such, okay? So I'm getting those two constraints as we see over here. So these are just scaling the constraints. Now, look at this. If the coefficients of, that means A1 plus 3A2 is greater than 6. What is 6? 10. This is 6. So I'm saying that if A1 plus 3A2, okay, is greater than or equal to this coefficient. And similarly, we do the same thing for the second part. So if A1 plus 3A2 is greater than or equal to 6, and A1 plus 2A2 is greater than or equal to 5, which was the coefficient of our objective function, x2 in objective function, okay? Then what I can say is that 5A1 plus 12A2, okay, will also be an upper bound on Z. Do you all agree with me? I'm saying that if the two constraints, I'm saying that if these two, the sum of these two and the sum of these two is greater than or equal to the coefficients, the coefficients of this guy, that's what we just did, right? I just showed you by example from 36, we went to 30, then 29. So I'm saying that if I multiply x1, constraint 1 by some constant value, which is non-negative, and constraint 2 by another constant value, which is non-negative, then the sum of these two coefficients should be greater than or equal to this, and the sum of these two coefficients greater than or equal to this, right? That means that this sum of the right-hand side of the constraints would be definitely an upper bound on Z. That's what we mean by the 36, the 30, and the 29 that we have obtained. Is it clear? I'm just trying to put it mathematically. I'm just trying to explain it mathematically. Okay? So,
Okay.
good. So this problem that we saw over here, where is he? Where is that good guy? Yes, this problem, okay? This actual problem, LP problem. This is the primal form, primal LP problem. I mean, this is the actual problem that we have, the primal problem, and now we want to obtain the dual. Okay, so this being the primal, let's look at the dual. Where is it? Okay, here. So, okay, so that we call the primal, okay? And then using that, I can now come up or reformulate another formula, a form of the problem, which is known as the dual form of the same problem, okay? And it is defined as such, okay? So this is the upper bound, as we all agreed that the sum of these two would be that bound which is actually moving towards our x star. So this is bound which we are trying to reduce and reduce until we get to this x star. Okay, so we are basically trying to minimize this bound, right? The value. So our dual problem would have a minimize, okay, this bound on Z, subject to, I just told you the sum of these two greater than equal to 6 and the sum of these two greater than equal to 5, which were, so 6 and 5 were the coefficients of the variables in the objective function in the primal form. Is it clear?
Yes.
So I
Clear.
get these two, and obviously
Yeah.
A1 and A2 are non-negative, which I already told you, which is written over here. So now this form is called the dual form. Interesting, right? I don't know whether I've been able to heat up your minds or not, but if your mind is now really getting hot, you should be expecting more further. So you still need some more patience. So basically, if you see, now what I've done is I have found an alternative way to solve this problem. And over here, it was a maximized problem where I'm increasing Z. And I've converted it into the constraints were less than equal to, okay? I've converted this into a problem where I want to minimize something, which was a bound on Z, and the constraints are now greater than equal to. Interesting?
Yes.
Okay, good. And then just for the sake of consistency, so that we do not mix up with this A1 and A2, let's say that the dual, instead of using the X variables, we use the Y variables, okay? So in the dual form, we can replace this A1 and A2 and write the whole thing in terms of the Y, okay? So when you have X's, it tells us that we are in the primal form. If you have Y's, decision variables written in Y's, that means it is the dual form, okay? So similarly, I just convert this guy into this. Oops, that's not a good arrow. This guy into this guy, where I'm replacing A1 with Y1 and A2 with Y2, just for the sake of consistency, okay? So it's the same thing. So keep in mind what happened. Maximize became minimize, less than equal to became greater than equal to. Now there's another thing that happened. Should I tell it now? No, I do not want to tell it now. We will see it later. Oh, I've mentioned it over here. Okay. So conclusion. For this simple example, where we have converted a primal LPP problem into its dual, what did we study or what did we observe? Number one, very important. If a problem can be written in the LPP form, which is a primal LPP problem, which we have studied so far, okay, and every primal problem has a dual. So that means every LPP problem that I give you, you should be able to obtain its dual. Okay? Check. Second, if the primal is a maximization problem, obviously the dual will be a minimization problem. We have seen that. Check. It says that if the constraints in the prime are less than equal to, then the dual is greater than equal to. We even saw that. Check. Now, if the prime has, this is important, keep in mind, if the primal has n constraints, its dual will have n decision variables. Keep that in mind. This is very important, okay? Very, very important. If your primal has n number of constraints, its dual should have n number of variables. So there's a relation between number of constraints and number of variables, okay? It's not constraints on both sides. So constraints on one side becomes variables and variables become constraints. Similarly, if the primal has m number of variables, the dual will have m number of constraints. Okay, so these words are related. So keep that in mind. This is very important. I'm repeating myself. Is it clear to everyone?
For example, here we have 3 constraints and 3 number of variables.
We do not have 3. We call this a default constraint. So we have basically 2.
Oh, okay.
Okay, so let's since you brought this up, let's go back and let's see what is the number of constraints. So over here in my primal, we have 2 variables, x1 and x2, and I have 2 constraints, 1 and 2, right? So number of variables is equal to number of constraints in dual. So 2 variables here, so I should have 2 constraints, which is true, right? 1, 2. I had 2 constraints up, and I should have 2 we are looking at this guy. Well, same thing. I had two constraints in the primal, so I should have two variables in the dual, y1, y2. Check. Is it clear?
Yes, yes.
Good.
Professor,
Yes.
is it like vice versa? If we have the primal that is minimization, is it dual going to be maximization?
Yes, because you don't know the formulation that you've got is primal or dual. By dual, I mean the alternative formulation. Okay, so if your problem is minimization, obviously it should be maximized. The dual will be maximized. These things are opposite each other. Exactly. So there should be, so basically I should write and vice versa over here as well. Okay. The next point is if the right hand side of the primal the right hand values of primal will be okay, yes, true. So again, we go back. Pay attention to this numbers over here. So we have this 5 and 12. Where did this come from? Okay, in the dual, we had this 5 and 12 in the objective, and this is actually this 5 and 12, the right-hand side of the constraints. Right? Now look at this 6 and 5. Now where do the 6 and 5 go? You can tell me. They go to, where is he?
The right-hand side?
Yes, the right-hand side of the dual. Interesting, right?
Yes, indeed.
Very good. So we saw these 5. Do we have any? Yes, there's one more. The coefficient matrix of the prime. The coefficient matrix of the primal will be the transpose of the dual. So if you write the coefficient matrix of the primal, okay, so basically by looking at this, so the coefficient matrix of this guy is 1, 3, 1, 2. So obviously, since it says the dual, so in the primal, it should have been 1, 1, 3, 2. Am I right? Let's take a look. Where are you? Here. 1, 1, 3, 2. So I'm right. So the coefficient matrix are transpose of each other. All right. These are very interesting observations that you have to, you have to know this by heart. So if you want to write in the matrix form, so the standard form for the primal would be, as I told you, we have in the matrix form, this should be actually C transpose. Let me write it down just to make sure that it's consistent. It should be less than equal to, okay? And in the dual form, you would have greater than equal to. So keep this in mind, okay? Now, one thing that you should be aware, you can say that, okay, this was a very easy example where everything was less than equal to in the primal formulation. So what happens if we have equality and actually greater than equal to? Well, hold your horses. We are going to look at that, and I think we can keep that for the next, because the next class, this is going to take long. It's like 3 pages.
Professor, so I have a question. So it's very interesting to have a dual form, but how does it help us in a way of
exactly. So if you have, say, a problem where you have n number of decision variables, which is n is, say, very large, okay, and you have fewer number of, let's say, 2 or 3 constraints, okay.
Yes, so we can interchange them and make lesser variables.
Exactly. You can interchange them, find the dual where you have lesser number of variables, and solving it would be much faster.
I see. Okay, thank you.
Okay. So actually, this is a very interesting question. And as I told you, like in reality, there are some problems, like in, for example, in my area, like networking, where you want to have resource allocation and you want to find optimal linear objective function. Solving it is very difficult when the number of nodes become very large in your network. So what you do is you just find the dual, which becomes very easy to solve given the computer speed that we have these days, and it gives us the same result. Okay. So we'll be looking,
Okay.
we'll be exploring the duality in more details next class. Okay, we'll be talking about the duality gap and whether actually the solution of the primal is equal to the solution of the dual or not. This is not always the case, and we'll look at what it means, like in terms. We'll try to interpret the mathematical behavior of these two forms. Okay.